Hello, my name is Bryan Reyes, and today I will be talking to you about Chapter 3, Section 3.1, which is about triangles, congruence, relations, and the SAS hypothesis. So we're going to begin this presentation by asking, what is a triangle? Typically, most people know it as a polygon, or they just say a triangle, but there is a more proper definition that the book states, which is a triangle is the union of three segments, called its sides, whose endpoints, called its vertices, are taken in pairs from a set of three non-collinear points. And below, I've put here an example that shows triangle ABC with the vertices of A, B, C, sides AB, BC, and CA, or AC. Now, what the diagram is showing is that there is an angle there at the corner of A, or point A, or vertex A, which, again, the diagram states that the vertex opposite of BC is A, or that the side opposite of A is BC, or that the included side of angle A and angle B is side AB, and that the included angle of sides AB and AC is angle A. So this is just to help demonstrate more visually what the definition of a triangle is that the book states. So now we ask ourselves, what is congruence? Most typically, and what we've learned in high school and a little bit in college, is that congruence typically talks about polygons that are the same size and the same shape, and they must be both in order to be congruent. And that's exactly what the slide is saying. Is that, however, the main similarity is that two shapes have to have the same size and the same shape in order to be considered congruent. We can see this through the three examples that I've given, which are these two rectangles, the purple and the green, that are the same size and the same shape, as well as the two pentagons and the two triangles. Each sets of these polygons are the same size and the same shape. However, this section is about triangles, so what we're going to talk about more so is about the congruence for triangles, their segments, and their angles. And the book states that the congruence for segments and angles is stated that the segments AB is congruent to XY if and only if AB is equal to XY. And this goes without saying for each of the segments, as well as the angles, in which angle ABC is congruent to angle XYZ, if and only if the measure of angle ABC is equal that to the measure of angle XYZ. And the other congruence is congruency for triangles, now that we've talked about the segments and angles. By definition, it says that if under some correspondence between the vertices of two triangles, corresponding sides and angles are congruent, the triangles are said to be congruent. So along with the congruency between triangles and their sides and their angles, we have the properties of congruence that typically also fall in under different categories of mathematics, but sticking to our geometric roots, we go by the reflexive symmetry and transitive law that specifically focus on congruency. So the reflexive law states that the triangle ABC is congruent to triangle ABC, or CBA. If this is not the case, then the two triangles are not congruent. The symmetry law states that if triangle ABC is congruent to triangle XYZ, then triangle XYZ is congruent to triangle ABC. If these cannot be written the same way or shown the same way, both in words and visually, then the two triangles are not symmetric. Now, with the transitive law, if the triangle ABC is congruent to triangle XYZ, and triangle XYZ is congruent to triangle UVW, then triangle ABC is congruent to triangle UVW. This does not hold that triangle ABC is congruent to triangle UVW if triangle ABC is not congruent to triangle XYZ, because for ABC to be congruent to UVW, it is that triangle ABC must be congruent to the middle or the second triangle out of the three in order to be congruent to the third. Much like saying triangle 1 is congruent to triangle 2 is congruent to triangle 3. If triangle 1 is not congruent to triangle 2, it is then that triangle 1 that is not congruent to triangle 3. And so one of the final things that is stated in the section, aside from a bunch of different examples stating the previous things that we've discussed, is the SAS hypothesis, or the side-angle-side hypothesis, which goes that under the correspondence of ABC, XYZ, let two sides and the included angle of triangle ABC be congruent, respectively, to the corresponding two sides and the included angle of triangle X, Y, and Z. So I've given an example here with two different triangles, a green and a purple one, whereas the one on the left has a tally mark on the left side as well as two tally marks on the bottom side of the triangle, and a curvature indicating that the angle that we are corresponding to these two sides is in between them, thus the side angle side. And we look at our green triangle, and the markings here are exactly the same as the one on the left, which would indicate that the sides with one tally mark on the green and one tally mark on the purple are the same length, as well as the curvature on the angle of the right of the green triangle is similar to the one on the purple triangle, which then indicates that those angles are congruent. And finally, we look at the other leg that has two tally marks on the green triangle, and we see that there are two tally marks on the purple triangle on the left, which then indicates that those sides are also the same length, thus showing that for each triangle, the side angle side hypothesis holds, and thus proves that these two triangles are in fact the same size and the same shape. So that concludes the presentation for section 3.1 of chapter 1. Thank you very much.